Okay, so just to give you a little bit of perspective about where we're going with this. So we said that models can either be deterministic or stochastic. And so if we know that the process we're trying to model has a significant stochastic piece to it, then we need to know how to model that stochasticity within our formulation. So what we might do is we might look at historical data for the process that we're modeling. And so that would be like coming up with a probability distribution from empirical evidence. So we look at it historically, see what's kind of happened, we plot our data in a histogram, and then look at the shape of that histogram and say, okay, this looks like such and such probability distribution, and so then in the future when we're making predictions about this process, we'll use that probability distribution to approximate the stochasticity that we've seen previously. So that's the idea. So then in this video we're going to see three useful probability distributions that arise pretty often in natural processes that we might want to model. So the first of those is the uniform distribution. And uniform distribution is where all outcomes are equally likely. So if your process is discrete, so let's say that your experiment has n outcomes, and we'll denote those with x1, x2, x3, all the way up through xn. Then the probability of any of those, so let's say the probability of some x sub k, well, if we've got the n outcomes and they're all equally likely, then the probability of any one is 1 out of n, so just one of the possible, so 1 out of total possibilities. And so a good example there is rolling a die, rolling a fair die. So if we're rolling a fair die, the probability of any number landing face up is 1 out of 6, since there are 6 faces. If the process you're modeling is continuous, then usually what happens is any outcome x within a certain range can be seen. So let's say that x can take on any real number between a and b. Here I've included a and b, but that doesn't necessarily have to be the case. So the probability then of any specific value, which I'll call x star in that interval, is going to be 1 over the length of the interval. So 1 over b minus a. And so the example here, and it maybe seems a little contrived, but let's say that you've got a line segment on a number line from 0 to 5, and you throw a dart at it and record the real number that the dart hits. Right, so let's say that you hit the number 2.1085. So the probability of that specific value is actually 1 over 5 minus 0, 1/5. That might seem a little counterintuitive to you, but you can think about why that might have to be the case. Okay, so the histograms for a uniform distribution, in theory, if you've got, your n different outcomes, so let's just say we're looking at the die example again. So we know our outcomes are 1, 2, 3, 4, 5, 6. If we roll that die, let's say 12 times, what we expect is that each one to come up twice, right? They're equally likely. So in 12 rolls, we should expect to see 2 of each outcome. So the histogram would be very even. What tends to happen is in practice, you don't exactly see that. So maybe what you see is something like we saw a 1, a couple 2s, a 3, a 4, a couple 5s, and maybe a 6, right? So it's not exactly even, but it's close enough that we say, okay, that looks approximately uniform, so we'll use that distribution to model whatever variation we see within the model. Second useful distribution is the normal distribution, which is sometimes called the Gaussian distribution. People typically, refer to this as the bell curve because of the shape of the histogram. So the normal distribution arises when most outcomes are clustered about one specific value. And that specific value is the population mean, which we denote with the Greek letter mu. And the population mean is something that we typically don't know, but we might have a good enough sense of just based on the theory behind our population, or if we've looked at a large enough sample, then the sample mean can approximate that population mean. And the further away from the mean that you are, the less likely that event is to happen. The probability is lower. So writing out a formula for the probability of any specific event isn't particularly helpful here because the formula is incredibly ugly and really difficult to compute by hand. So typically we compute probabilities using technology. In the very old days they used tables to do this, but technology is even better than the tables, so that's what we'll do in a later lesson. But for now I want to show you the histogram, which I'm also going to refer to now as the probability density function. And the reason that I can switch at this point is because instead of the absolute frequency on the vertical axis, I'm going to plot the relative frequency. So in terms of the uniform distribution that we talked about a minute ago, here I plotted the absolute frequency, right? So I saw 2 1s, 2 2s, 2 3s, so on and so forth. If instead I had normalized this, so I said 2 out of the 12 were 1s, 2 out of the 12 were 2s, so on and so forth, that's now the relative frequency. So that's when you're getting a fraction or a decimal, or you could represent it as a percent, which then corresponds to the probability of seeing any of these things. And so once you plot that relative frequency or probability along the vertical axis, now you can call this either a histogram still or a probability density function, which is sometimes shortened to PDF. Alright, so the probability density function for the normal distribution has this bell curve shape, so it's symmetric about the mean, and then it goes off in tails as you move further away from the mean. The probability gets smaller. And these inflection points, so where the graph changes concavity, is one what we call standard deviation away from the mean. And standard deviation is denoted by this lowercase sigma. So oftentimes you'll see the notation that something is normal with mean mu, standard deviation sigma. And standard deviation is something that, again, we can use technology to compute from a population sample. But the basic idea behind standard deviation is if you take all of your data values and compute their respective distances from the mean, and then take some sort of average of those, then you get the standard deviation. So think of it as the average distance away from the mean that your data values lie. One thing that I should specify is that there are infinitely many normal distributions, right, all with different mu and sigma. But once you know a mu and a sigma, then you know which normal distribution you're referring to. Also, I've drawn this sort of continuously, but we could have it discrete, right? So these are just going to be then bars sitting in here. And again, it may not be exact, right? Sometimes we might overshoot or undershoot. But in the end, if what we have is approximately bell-shaped, then we're pretty much fine in using the normal distribution to approximate our stochasticity. Okay, so then the last of our useful distributions is the binomial. And it's called such because we have some sort of probabilistic experiment with only two outcomes. And then we're going to complete this experiment a fixed number of times. And we'll call it n as our number of times. The outcomes we often refer to as either successes or failures, just because there are two of them, and it doesn't have to be that one is necessarily better than the other. It's just usually a success is what we're interested in seeing for some reason, and a failure is just whatever else. The probability of a success we denote with lowercase p, and we assume that this is a fixed probability. So from one experiment to the next, or one trial to the next within our n different trials, the probability of that success won't change. The probability of a failure is denoted with lowercase q, and that turns out to be 1 minus p. Right, since there are only two outcomes and something has to happen with probability 1 for every trial, then if success is probability p, failure is probability 1 minus p. So an example would be something like we've got a robot shooting 3 free throws, and the robot's going to do that 3 times. And let's say that the probability that the robot successfully makes the shot is 0.6. So that the probability that the robot misses is going to be 0.4. We might be interested in the probability of making 2 of those shots successfully. So one thing to think about is each shot, like we said, since the probability doesn't change from one to the next, each shot is independent. So if the robot makes one of them, that's probability 0.6. If the robot makes another one, that's another probability of 0.6. So we just multiply those two because of the independence. And then the robot has missed one with probability 0.4. But then you have to consider the fact that there are different ways the robot could have made 2 of the 3 shots, right? So the robot could have successfully made the first 2 and missed the third, or missed the first and successfully made the last 2, or it was successful in the first and third and not the second. So to account for all of those different orderings of successes, we use the binomial coefficient, indicated this way, which is often read 3 choose 2. Sometimes this is called a combination. And 3 choose 2, so this gives us the number of ways to choose 2 of the 3 shots to be successful. and that's 3 factorial over 2 factorial times 3 minus 2 factorial, which in this case is just 3, and it's the 3 ways that I named off a minute ago. So once we do this multiplication, we'll have the probability that this robot successfully makes 2 of the free throws. So now in general, what I'm going to do is change all of this for the general case. Give me just 1 second. All right, so let's suppose that we want to know the probability of k successes in n trials. Then we're going to do n choose k, where again n choose k is n factorial over k factorial times n minus k factorial. Then you take p to the k power because k of those trials were successful with probability p, and then the remaining n minus k trials were not successful with probability q. So in terms of what the probability density function or histogram looks like in this case, I'm going to get rid of some of this just to free up some room. So it looks a lot like a normal distribution. One way in which it's different is that the normal distribution, and it's hard to see the way that I've drawn the normal curve above, but normal distribution goes forever in both directions, which means that at some point it takes on negative values for sure. You know, here I've drawn it, it kind of looks like this is the origin, so that the mu is positive. But mu could be 0 or mu could be negative even, but in any case it goes forever in both directions. Binomial, remember, we're looking at probability of k successes out of n trials. So it's not possible to have fewer than 0 successes, and it's not possible to have more than n successes out of n trials. So the distribution has to stay between 0 and n. But then otherwise it can look pretty much the same as a normal curve. So it could be, wanted that to be more symmetric. So yeah, it could be symmetric with its peak in the center. That's not going to be much better, but whatever. It could be that the peak is on the left, and then there's a long tail on the right. So when there's a tail on the right, we call that right skewed. And it could also be the case that we have the peak on the right with a tail on the left, in which case we call that a left skewed distribution. And so in the exercises you explore a little bit when the peak is in the center versus to the left versus to the right, what kind of indicates that in terms of your binomial problem. But that's it for now. So thanks so much for putting up with the video issues before, if you did. And if not, hopefully this one was helpful.